Just some new precedents, to look at some projects that we're doing to give you a sense of how far we're stretching. The City Point project is an 1,100-foot tall building that we're actually building in a suburb in Brooklyn, New York, of all places. The middle project, the Standard, is actually a high-end boutique hotel designed by Polshik and Partners. The developer is Andre Balaz, who's a fairly well-known boutique hotel developer. It's being constructed and bridging over an old and dilapidated rail line in the meatpacking district. The media conglomerate IAC recently built a Geary design project on an old brownfield site on Manhattan's west side. And Raphael Vignoli is doing an 8-building mega project on the site of the former Domino sugar factory. So we're really stretching in Manhattan right now to find places to build on. The project I want to present for this particular case study is 610 Lex. This is a quintessential New York development in terms of its complexity and moving parts. It's a 61-story building, turns out to be 740 feet, 9-story podium, 3 levels below ground. Total square footage is only 250,000 square feet. Architects Foster and Partners, developers are important on this one, RFR Realty and Hines. We are obviously the structural engineers with Turner as the contractor. The site itself is small. It's only 10,000 square feet on the corner of 53rd and Lexington. The interesting part of this project, and why I call it sort of quintessential New York, is that development rights were shifted from Mies van der Rohe's Seagram building, which RFR owns adjacent to the site. Unused air rights were also transferred along with a plaza bonus from the Lever House, which RFR also controls across the street. And that increased the total square footage that we could build on the site from 175,000 up to 250,000, giving us an equivalent FAR on the site of almost 25. That's pretty dense. The site is also encumbered on both sides by the MTA, and the approval process was rather extensive. One other complication to add insult to injury was the fact that Hines, co-developer on the project, owned the adjacent building, 600 Lex, and they imposed an additional light and air easement on the site, which prohibited us from building over at least half of the width of the site, okay? One more complication. Sky exposure plane requirements of New York, which essentially prohibits building up to the street line to prevent sort of the concrete jungle creation. It's essentially a diagonal line that you can't build past. When we look at all of those constraints and we try to build out the 250,000 square foot, we wound up with an incredibly slender tower. The width is 45 feet, the height is 740 feet. The footprint is only 355 square meter, okay? Aspect ratio is 16.5. I'm not aware of another building with a ratio that high. Wrong way. Foundations, we're using 36-inch diameter caissons to rock. Tower gravity frame is typical New York flat plate, 10-inch conventionally reinforced concrete slab. The tower lateral frame is just shear walls, very, very simple. What we did here, though, is we pre-tensioned the shear walls as well, and I'll get into that. We've got belt walls mid-height and at the top, and we're using high-strength concrete on the order of 100 megapascals or 14 KSI. Tower levels, you can see, very, very small, very simple in terms of the form of the lateral system, cross-block shear walls with large bulbs on the end. The vertical post-tensioning, which is something that we had never tried, but we needed to try on this project to make it work, actually, did 3 things for us. It eliminated the net tension in the wall, which allowed us to use, from a stiffness standpoint, the full effective section properties of the wall, significantly reduced the amount of reinforcing. And for you structural engineers, we were on average on the order of about 1.5% reinforcing up the height of the building, which is really low. And an interesting sort of byproduct is because the PT force acts along the centroid of the walls and the elements, it actually reduced or had a countering effect to the P delta moment and displacement magnification. One thing that we had to do, a little trick, is develop a link across an atrium to the low-rise portion of the building, and it essentially cut down the effective height of the building and gave us some performance and some displacements that were a little more tolerable. Again, this is the prop level. You can see how it ties across the atrium. Talk about the wind tunnel study for a minute. We established a target building response of 18 milligis. There's some debate as to whether it should be 18 or 15. We thought 15 was simply impractical for a building of this aspect ratio. We simulated the response, assuming 1.5% damping, with a resulting building acceleration of 25 milligis. We looked at various damping scenarios, including a slosh tank, tuned mass damper. We came up working with RWDI and Motioneering, a dual symmetric damper, provided up to 4% damping, and the resulting building response got down to 18 milligis, which we felt for this type of project was acceptable. Little graphic, you like that? There's actually two dampers. And again, I don't know of another building with this kind of application. They're located on each side of the elevator core, behind the glass curtain wall up top. They're two 375-ton folded pendulum tuned mass dampers. And you can see that graphic there. Next project, I'm going to sort of glaze over this only because it's in San Francisco, and you're going to hear a lot about that city. 59-story building, 645 feet tall, three-story podium structure, 5 levels of below-grade parking. Again, all that we build below grade doesn't count against total buildable above grade, so it really becomes a necessary solution for us. About 1 million square feet of new construction. Architects Handel and Associates, Millennium Partners developer, where the structural engineers, Webcourse, a contractor. And again, San Francisco, not typically what we consider, coming from New York, a dense city, but over the years it has become. Just some structural stats. The building's the tallest reinforced concrete building in a Zone 4 or equivalent, and is now the fourth tallest structure in San Francisco. You can see the excavation, 5 subgrade levels, 60 feet below grade. We actually use C-count walls for the bracing of the excavation here. Again, tight site, not one normally found in San Francisco. Foundations, we had 945 14-inch precast piles. Supporting a monolithic mat that supported the tower. Lateral system is dual system, concrete cores, partial perimeter moment frames. And again, we're going to get into that. I know Ron's going to talk about this at length, so just to give you a sense of what the tower itself looks like. Tower to the left is the high-rise portion. Tower to the right, is the low-rise portion. I got that. Just some particulars of the job that we find interesting. The link beams tying the shear walls themselves together, we used steel embedded shapes. That was primarily a function of the architect and owner's desire to reduce the depth of those beams. I know somebody else, I think Hans Baumann is here. He's going to talk later about the use of Bowgrid. But that graphic, I think, speaks for itself. In lieu of using conventionally tied reinforcing steel for the columns, the shear walls, and the moment frame beams, we used a pre-manufactured, pre-welded confinement steel. It was 1-to-1 ratio. It had actually been approved by the city and somewhat disapproved at the time of our permitting process, which added a bit of a wrinkle in that we then had to test the effectiveness of the Bowgrid, and it did pass. Next project, and this is one of my favorites, is the Cosmopolitan. It's actually located in Las Vegas. It's 2 towers, 50 stories, 650 feet in total height. It'll actually be the tallest building in Las Vegas when it's completed outside, or if you exclude the Space Needle there. It's got a 6-story podium housing ballroom, theaters, and casinos. It's got 5 stories below grade. Again, never been done in Las Vegas. 6.5 million square feet. Architect is Bernardo Brescia at Arquitectonica with Friedmutter Group locally. developers Continuum, we're the structural engineers, and Perini is the contractor. This is an interesting study because I think it sort of hammers home my point really well. This became a very tight urban site on the Strip. It was actually an afterthought and a piece of land that nobody wanted that was stuck between the Bellagio and MGM's new city center project. It's actually adjacent to and slides somewhat between those two low-rise buildings called the Jockey Club. Vegas has undergone an incredible transformation recently. I think when we opened our office about 3 years ago, there was some 82 high-rise projects planned. Of those 82, only about half of them went forward. Vegas is a gaming town. The majority of the activity is gaming related. Currently, outside of the Cosmo and the work that we're doing on MGM City Center, we've got about 20 million square feet of projects on the boards, another 15 million square feet in the wings, and there's another 20 million, at least that we know of, that's being planned. Land prices have soared. 5 years ago, an acre on the Strip with Strip frontage ran $1 million. The Allowed Group, who just bought the Frontier, spent $30 million per acre. So land is definitely at a premium in Las Vegas. Go figure. Just to give you some context, the Monte Carlo, which is an existing hotel casino, occupies some 22 acres of land, and it encompasses about 4.5 million square feet. The Cosmopolitan is 6.5 million square feet, and it occupies only 8.5 acres. Okay? To do that, we really had to think differently about our solution and come up with something more vertically stacked. In Las Vegas, typically, everything comes down to grade. You've got a hotel tower in concrete, fill-in space in structural steel with no transfers, and then a standalone parking garage. Given the tightness of the site that we had, we really had to start thinking differently and introducing different ways of building in Las Vegas. Just to look at the stacking a little bit, again, you've got 5 levels of parking, casino on the ground floor, hotel lobby and shopping on the 2nd floor, convention space on the 3rd floor, pre-function and ballroom on the 4th floor, and then a large pool and what they're calling an adult playground. Don't ask me what that means, on the roof of the sky deck. And then we go up 65 stories with a concrete tower. Interesting enough, in Las Vegas, there's tons of water below grade. 13 feet actually below grade, you've got significant groundwater. To get the amount of parking required by code and without incurring or taking away from the FAR that we could build above grade, we went down 5 levels with a total excavation depth of 75 feet. To do that, we introduced a slurry wall technique. Again, never had been done in Vegas. We got some pretty strange looks when we proposed it originally, but having worked with Perini on the East Coast in Boston, they were very familiar with the technique, and they embraced it eventually. Facilitated a much deeper excavation, and what was great about it is acted as a cutoff wall, eliminating the need for us to dewater the site during construction. So again, significant cost savings by the elimination of that. And again, the foundation wall became the slurry wall, so there was no need to pour an additional wall. Interesting in that we were going down 75 feet. The conventional foundation system for Las Vegas is typically a drilled caisson. In that we took out 75 feet of soil and rock, we were able to eliminate the need to go to caissons and actually put the building on a mat. What we did have to do, however, and this takes a little explanation, is actually pre-compress the soil that would be under the high-rise portion of the building. And we did that because the soil itself actually has a tendency to rebound once it's unloaded. So if it rebounded up, I think the prediction was 3 inches. We were predicting at least 2 inches beyond the rebound point. So to submit the building itself to over 5 inches of total settlement was unaccepted. And as such, we came up with the pre-compression technique. Structural steel was used at the podium, cleverly procured from Asia at a bit of a discount. Our Hong Kong office actually provided QA support overseas. And the project itself utilizes about 45,000 tons of steel. It's a significant steel project. One of the things that's interesting about the vertical solution is that the entire lateral system of the 65-story concrete tower had to be transferred out at the top floor of the podium. All of the space under the tower was to be used for casino and retail, and as such, all of the shear walls had to come out. The amount of force associated with the wind and seismic loads, coupled with the fact that it became a discontinuous lateral system, really increased the shear demand on the building that was left below the podium. We wound up coming up with a fairly clever solution that was a composite steel and concrete shear wall. You can see on the right, they're actually dropping prefabricated panels, sliding them in place between columns. They were welded and then filled with concrete. And all of those were actually located out on the perimeter walls along the lot lines adjacent to the existing buildings. In terms of bringing the gravity and lateral frame down at the top of the podium, we used a technique that we've used before. We call it a sky mat. It's actually a 7-foot thick concrete transfer slab supported on composite steel box columns. The mat was poured in actually 3 lifts to prevent the contractor from having to provide shoring for a 7-foot thick concrete slab. You can actually see the ladder coming up adjacent to the crane. That's the steps up to the top of that mat. So, simple. Tower gravity, again, traditional sort of 9-inch post-tension flat slabs with shear walls going through the room demise. You can see actually the tower's coming up. It's about 3 levels above the podium. One Bayfront Plaza is another project that's interesting to me. I'm going to rush through it because I realize I only have 2 minutes. And again, architects Terra, developers Florida East Coast Realty, we're the engineers. Just to give you a brief on building in Florida, what they've done over the years in Florida is, you like that, huh? What they've done in Florida is instead of addressing things like construction quality, each time we have a significant hurricane, the writers of the codes locally take it upon themselves to merely increase the wind speed and the wind force. Currently in downtown Miami, the design basis wind speed is 150 miles an hour, which comes out on average to about 120 pounds a square foot structural frame load. It's significant. Oakston proximity requires us to think about storm surge, and candidly, the soil conditions there are really not conducive to high-rise construction. Just to look at some progression, we've been doing business down in Miami for decades. My dad actually did the first modern skyscraper in the 70s. The Marquee is 700 feet. Four Seasons is at 800. Bayfront has got 2 towers at 840 and over 1,100 feet. So again, in an area you wouldn't think you'd want to build tall in, we're being forced to build tall in. Look at the plans. Foundations are 5-foot diameter, drilled caissons extending about 100 feet deep. Got a 12 to 15-foot mat depending on where we're at. The perimeter columns are simply supported on very, very simple caissons with caisson caps. This is something that we learned from our experience at the Four Seasons, which is currently the tallest building at about 800 feet in Miami. We could not practically build this building at about 1,100 feet using an all-concrete system. There's no way that we could get enough caissons within the footprint of the tower to support the loads associated with an all-concrete scheme. We're going with a composite scheme, which will be the first of its kind in South Florida, consisting of concrete shear walls and steel gravity frame, gravity columns, as well as perimeter bracing. That's it for the project. I had to rush through it, I'm sorry. In closing, conclusions. I think that what we're seeing here in Dubai is rather unique. Will Dubai become anything like New York in the next 20 or 30 years? That'll be interesting to see. Will you be faced with the same kind of challenges that we are? It'll be interesting to see. But there's some things that we need to address. You know, building tall for the sake of building tall is one thing, but can we utilize tall and big solutions to a sustainable end? I think we've been talking a lot about this at that conference. And the other thing is designers of future cities need to address a spectrum of urban issues, such as densities and massing, within a more coherent framework to fully utilize the available resources. New York, at least from my experience, has really been piecemeal in terms of its planning, and as such, we wind up with buildings like 610 Lex, which I just presented. Thank you.